Hello, dear colleagues. Let me present results of our project. Our project is a fair comparison of ECO-DQN and Struczvee-DQN methods. Our team is Nina Mazявkina, Svetlana Illarionova, and I'm Mikhail Gasanov. Problem statement. Number of real-world problems can be reduced to graph combinatorial optimization problem. There are number of traditional NP hard solvers. Sometimes they require, it's very time-consuming and requires specialized knowledge. And last few years, machine learning approach to this problem were developed. In our work, we are going to consider some of these works which apply reinforcement learning techniques to optimization problem. Objectives of our work: at first, to analyze the latest developments in graph neural network area. Second, to reproduce results of papers Struczvee-DQN and ECO-DQN. Estimate reduction strategy for max cut and free sub problems. And conduct experiments with different reinforcement learning methods for solving max cut problem and ECO-DQN and Struczvee settings. A few words about graph neural networks. Graph neural networks allow us to represent nodes and edges of graphs in embedding space. As in word-to-vec approach, we want to represent similar words closer to each other in embedding space. In model graph neural networks, we do assumption that our nodes, which are closer to each other and play similar roles in graphs, will be close to each other in embedding space. In papers, authors used Struczvee approach. A few key ideas about this approach. First main idea that we want to find similar nodes in a graph which play similar roles. First, its neighbor nodes can be different, but faraway nodes can be similar, and this approach allows us to analyze depth of similarity for the graph. How it works? Let's consider some graph with diameter k6. At first stage, we need to analyze number of vertices neighbors in first circle, second hop in second circle, third hop, etc., etc. If we want to compare two different nodes, analyze their similarity, let's consider example for this graph again and for second hop, second circle. Here we need to estimate number of nodes in second, number of vertices in second circle of this graph. For node U it's 8, for node V it's 3. After, we need to do a sequence of their degrees of these nodes and apply dynamic time wrapping technique to obtain distance between these two nodes. Next step, we generate multi-layer graphs. At each layer of this graph, we have our step of analysis of our nodes, and edges of our multi-layer graphs has these weights. In research, Struczvee-DQN authors applied this Struczvee technique, and in their deep network for arbitrary graph, they received embeddings for graph with 2 or more layers network, and iteration by iteration selected best possible nodes and add them in the best solution, better solution. NP-hard problems is a set of problems to which any problem from NP class can be reduced in polynomial time Here are the same well-known problems. For example, minimum vertex cover, max cut, traveling salesman problem. Let's consider NP-hard solvers on the example of satisfiability set problem. In set problem, we have a Boolean formula in conjunction normal form. We aim to verify whether there is such assignment, then formula equal to 1. There are several approaches to solve it. The main weakness of the naive approach, it's brute force, it's time consuming, especially in real life problems. It requires a huge amount of, there are a huge amount of variables, and it requires a huge amount of time. There are some heuristics created to make solution solver faster. A simple example of heuristics when we want to find some conflict to reduce searching space. And motivation of our work is that there are a number of papers published in recent years that considering combinatorial optimization tasks. However, as usual, authors focus on solving one type of problems and do suggestion that their algorithm might perform well in other NP-hard problems. That's why it's difficult to compare some approaches described in recent work. We aim to analyze the way how FreeSAT problem can be reduced to MaxSAT. It allows to evaluate performance of different models using independent set of NP-hard problem benchmarks, and in future it will be possible to compare different reinforcement learning methods to different NP-hard problems. Yes.
So another part of our project was actually adding and trying out different reinforcement learning methods in ECO and Struczvee training settings. As the candidates for those methods, we have tried out proximal policy optimization and soft actor critic, which both belong to policy gradient methods, but soft actor critic actually is also off policy. So on the next slide, you can see the way to reformulate the MaxCut problem in a MDP and reinforcement learning setting. So we need to define a set of states, which is our currently chosen solution or cut. We need to define the set of actions, which is adding a new edge to the set. And the reward function is going to be, in the discrete case of MaxCut, is the difference between the sizes of the solutions of the current solution that we have and the best solution that we have received so far. So this setting is used in Struczvee paper, but ECO-DQN authors suggest to improve the training process and improve this formulation by adding the additional action of removing the edges from the current solution and adding some small rewards for exploration of the new states. On the next slide, you can see the results that we have received for both of ECO and Struczvee settings. And here you can see that although unfortunately both of the algorithms underperform compared to original ECO-DQN, we can see that proximal policy optimization actually manages to learn higher valued scores of higher valued cuts after 1 million time steps, and soft actor critic, although unfortunately it oscillates around one value, you will see from the project report and you will see from the lost functions on the project reports that the loss actually decreases and the network manages to learn something. On the next slide, you can see the same results for Struczvee setting, and proximal policy optimization here curve is much noisier. However, our hypothesis for this is that as policy gradient methods are very simple and efficient, and they depend on the high frequency of positive rewards, general Struczvee setting with its sparse reward doesn't provide any stabilization for our training process. Unfortunately, for soft actor critic, we have encountered the exploding grading problem, that we haven't managed to solve for now. And on the next slide, you can see the comparison of our methods to the greedy solver. This is reminiscent of what has been done by the authors of the original paper on ECO-DQN. And so we are taking some 50 random initializations of 5 different graphs and take the best maximum, the best cuts that we have received. And on the next slide, you can see the mean of the cuts from this array of the solutions. These results follow the same pattern as the training results. And in conclusion, on the next slide, although we have trained both of the very powerful reinforcement learning methods, we have received worse results than the original paper, but we could manage to get some very interesting and very useful findings about the training process and about the details of all of these reinforcement learning methods. As the conclusion for our project, on the next slide, we have managed to replicate the results of the original DQN and Struczvee papers, show the reduction of the, by the example of 3-set problem to max cut formulation, analyze the graph neural networks, and implement several other reinforcement learning methods for ECO-DQN and Struczvee. On the other part of the slide, you can see our further plans for this project. And thank you for your attention. So